Here's where I'm not going to say the method breaks down. It just gets a little more involved. So let's try to integrate here. E to the negative x cosine of x dx. These types of functions are really important because they represent damped oscillations. So let's take a look at this function before we integrate it. I'm gonna alter it here so we can we can see what I'm talking about here. So we know the cosine wave oscillates infinitely, and it always goes between -1 and 1. And so when you multiply it by a function, you can think of that function as the amplitude of that wave. So if I graph e to the negative 0.1x and e to the 0.1x, negative 0.1x, you see what's happening here is that these exponential functions are attenuating that curve. Okay? So if you have like a frequency or broadcasting, it's not going to always have the same amplitude. The amplitude will decay as the energy decays. So these types of functions are really important. So let's see how we integrate them. The integral e to the negative x cosine x dx. Now looking at our pecking order here, if I look at the factors, I've got the e to the negative x, that's an exponential factor. The cosine of x is a trigonometric factor. So if you notice, the trigonometric factor narrowly beats out the exponential factor. And once again, why these are at the bottom tier here, we're going to see in this example. So I'm going to let u be the trig part based on the rule of thumb. And then my du, I'm going to calculate to be negative sine x dx. My dv then is going to be whatever's left over when I cover up the cosine, which is e to the minus x dx. When I integrate that e to the negative x, remember that's a negative 1x. I'd be dividing by negative 1, which I'm going to pick up a negative there. And now I'm going to apply the formula here. It's u times v, so a negative e to the negative x cosine x minus the integral of v du. Notice here we've got a negative e to the negative x times a negative sine of x. So those two negatives cancel out. And now we ask ourselves, looking at the integral I started with, and looking at the integral I have now, is it somehow easier? And the answer is no, it's not easier because you still have essentially the same thing going on there. It's no harder than what you started with, but it's not any easier. So at this point, what do? Well, right, Einstein said insanity is doing the same thing again and expecting different results. So we're going to go a little nuts here. We're going to do integration by parts on the next one, on the e to the negative x sine x, and see, fingers crossed, if something different happens. So using the same rules of thumb, the trigonometry narrowly beats out the exponential. I'll let u be the trigonometric. The dv be the exponential. The du here produces a positive cosine x dx. The v is going to be the same as before. And the rain has come. The rain has come. I think all the cats are inside. Yep. They're all looking outside now. So I've got the uv minus the integral of v du. Now, I'll put that in there here. Oops, we got to be very careful with the plus and minus here, folks. So I get negative e to the minus x sine of x, and then I get a plus the integral e to the minus x cosine of x dx. Now, does this integral look familiar? It should. That's the integral we started with. So this integral has lapped itself. It's come back to itself. So I call these integrals, my little pet name for them, and this is not official, I call these wraparounds. Okay? I call these wraparounds because they wrap back to themselves. Now, let's see what happens. Let's see what happens when we substitute that into here. So let's take, oops, I didn't want that. I want to put it here. So the integral e to the negative x cosine of x dx equals what? Negative e to the minus x cosine x minus the integral e to the negative x sine x dx. And now I'm going to replace this integral with what I've got here. So I get, I'm going to over here, minus e to the minus x cosine x minus the quantity minus e to the minus x sine x plus the integral of e to the negative x cosine x dx. So notice, here's what I'm trying to find. I'm trying to find what that thing is, and I've noticed that it's now coming on the other side of the equation. So let's just, to help us see the forest for the trees, let's call this big thing I. And what we've got is the integral I that we care about is equal to negative e to the minus x cosine x plus e to the minus x sine x minus that integral I. So think about this as an algebra problem now, folks. I'm trying to figure out what I is. I've got I over here, I over here. I can add I to both sides. So I'd have 2 times I equals this. And I'm going to go ahead and put the sign part first because it's positive. Okay. And so then to get what I is, I just have to take both sides and divide by 2. Is everyone okay with that algebra there? So the fact that it came back to itself was actually very helpful, because now I can get at it that way. So my final answer will be the integral from e to the minus x cosine of x dx is equal to e to the minus x sine x minus e to the minus x cosine x all over 2. And don't forget your what here, folks? Plus c. Okay? Because technically speaking, this integral represents a family of antiderivatives. This integral represents the same family of antiderivatives. Any two members of those families are off by a constant. So then when we quote add things to both sides and these quote unquote cancel out, they could be off by a constant there. So the plus c is actually floating all the way through this. We just don't write it down until the end. All right. So that's an example of a wraparound integration by parts. Are there any questions on it? So if the integral you get is no more difficult, give it another try and see if it comes back to itself. Now, another integral like this is the integral of secant cubed x dx. This is the classic example. We'll work through this one together. And then at the end, when it's all said and done, we'll look at what this answer works out to be, and we'll find an easier way to remember it. This integral, interestingly enough, comes up more often than you may think. All right. We're going to see at the end of the course if we're trying to measure the length of a parabola. So if you had an actual parabola trying to measure the length of it, this integral pops up, believe it or not. So in order to do parts on this, I need to break it down. And now I'm kind of motivated by the dv portion. We're going to rewrite this first. If you try parts as is, you might want to let u be all of secant cubed, dv is dx, and then you find your du and your v make things a lot more complicated. So let's split this off, and now we've got trig versus trig, right? We got two trig functions. I'm going to let u be this and dv be that. Why? Because this is easy to integrate. The du then is the derivative here, secant of x times tangent of x dx. The v then, you integrate, suppress the constant of integration, you get the tangent. And so we get the u times v minus the integral v du. So I've got a secant x, tangent x times tangent x. That's tangent squared x. Now, is the integral we have here any more complicated than when we had before? Well, you might say yes, because now we have secants and tangents, but we're going to do a little preview of Friday. Friday, we're going to be talking about trigonometric integrals. And we're going to be talking about using Pythagorean theorems to convert trig functions back and forth. So you may recall that tangent squared and secant squared are related. Tangent squared x can be written as secant squared x minus 1. That's a Pythagorean identity. And so what I can do is substitute that in for tangent squared. Why would I do such a thing? Because now I've got secant x times secant squared. That's going to get me back to my secant cubed integral. So let's put all this together on the next slide. Before I do that, though, is everyone following the parts and the identity there? So putting this all together, I've got the integral secant cubed x dx equals secant of x times tangent of x minus the integral of secant x times tangent squared x, but that's going to be secant x times secant squared x minus 1. And so once again, giving myself some room here. That's secant x times tangent x minus the integral of secant cubed x dx. And now we've got a minus, so that's a plus integral secant x dx. And now we're in the same situation we were in the last example, where the integral we want is appearing on both sides of the equal sign. So I'm going to add this to both sides. I'll double it up. So I'm going to be left with 2 integral secant cubed x dx is equal to secant x times tangent x the integral of secant x, remember that's natural log absolute value, secant x plus tangent x. So to get the integral of secant cubed all on its own, I'm just going to take my answer here and divide it by 2. Secant x times tangent x plus the natural log of the absolute value, secant of x plus tangent of x all over 2. And then, of course, we arbitrary constant floating around there, plus c. Okay? Other application of parts takes you back to where you started. So, any questions on this? Do you see how the stuff moves around? There's a couple of these on the homework. Anytime you're letting your u's be trig functions or exponentials, you can expect this sort of behavior. Because when you take derivatives of exponentials and circular functions, you get exponentials and circular functions. Now, I mentioned that there was an easy way to remember this formula, and here's the way I remember this formula. And henceforth, anytime you're integrating a secant cubed, you can use this formula. You don't need to go through the parts again. You might notice that the first term here is the derivative of secant, and the second term here, well, that's the integral of secant. And what am I doing with those two things? We're adding them together and dividing by 2. In other words, we're taking their what? Average. So I think of this as the average of the derivative of secant and the antiderivative, or the integral of secant. That's how I remember the integral of secant cubed. Hopefully that's easy enough for you to remember. Once again, from here on out, anytime you've got integral of secant cubed, don't go through the parts, hit it with this.